So we're going to go ahead and start with problem number 1. So let's take a look at problem number 1. A roller coaster ride at an amusement park lifts its car of mass 700 kilograms to a point A at a height of 90 meters above the lowest point on the track, as shown above. The car starts from rest at point A, rolls with negligible friction down the track, as shown above. Oh, goodness. So let's go ahead and start with problem number 1. Okay. So we have a roller coaster ride at an amusement park that lifts a car of mass 700 kilograms to a point A at a height of 90 meters above the lowest point on the track. The car starts from rest at point A, rolls with negligible friction. Go ahead and say negligible friction so we won't have to take it into account. Down the incline and follows the track around a loop of radius 20 meters. Point B is the highest point on the loop and is about 50 meters above the lowest point on the track. So, for part A, it asks us to indicate on the figure the point P at which the maximum speed of the car is attained. Well, due to the conservation of energy, we can go ahead and say that the maximum speed is right here at point P. This is going to be the maximum speed, right? That's the first thing that's pretty easy. So we've got number 1. For A, the second part of part A, it says calculate this value of this maximum speed. So let's go ahead and take a look at this. I've drawn out a trusty section of this track so that we can go ahead and do our work here in some space. So the roller cart came up, and we know that at point P, so for part A in this question, we know that 1 was point P is indicated at the bottom of this first hill. Question 2 asks, what is the value V max? So to answer that question, we have a rather simple question of the conservation of energy. We know that the initial energy is going to be equal to the final energy, and we know that the maximum potential energy occurs at point A, and then the maximum kinetic energy occurs at point P, and we can say that there's no kinetic energy at point A because it starts from rest, and then there is no potential energy because we'll call this the height 0. So we'll say that all of the potential energy has been converted into kinetic energy there. So the potential energy initially is going to be equal to the kinetic energy at the end. So if we remember, mass times gravity times height gives us 1/2 mv squared. And when we solve through, we see that the masses will cancel out, and we'll get 2gh equals v squared, which means our velocity is just going to be the square root of 2gh. A simple substitution of our values into this equation gives us the velocity is going to be twice the gravity. On the free response, we'll use 9.8 meters per second squared for the gravity, and then the height is 90 meters. So if we do our calculation correctly, we should see that the velocity here is going to be 42 meters per second. All right, so we found the maximum velocity. Now, let's look and see what the next question is here. So part B says so we've figured that out. Part B says to calculate the speed VB of the car up here at point B at the top of the circle. Now, what we can do is why not keep this a conservation of energy question as well. So if I'm answering B, I look and say, okay, all of the potential energy is converted into kinetic energy here, and then some of it, as it goes up, the potential energy starts building again, and at part B, because it's below part A, there is going to be kinetic energy, and because it's off the ground, there's going to be potential energy. But the same as before, we know that initial energy is equal to the final energy, and the initial energy, all of the mechanical energy in the system is at point A, the potential energy at point A. So our initial potential energy is going to be equal to the potential energy at point B plus the kinetic energy at point B. And as we make a very simple substitution here, we will see that mgh at A is going to be equal to mgh at B plus 1/2 mv squared. And that is going to give us the velocity at point B. So if we do some simple algebra, we can see that and as we see before, you guys might see a pattern. This equation looks very similar because all we have is potential energy being converted into kinetic energy. And the same is true whether the delta H is from the top to the bottom for a maximum or from the top just down to point B, which is here. So let's see, if we know that the velocity is going to be twice, the square root of twice the gravity times the change in height, we know that the gravity is 9.8 meters per second squared, and the change in height here is going to be the height at A minus the height at B. The height at A is 90 meters. The height at B is 50 meters. 90 minus 50 gives us 40 meters. And so we just plug in the 40 meters, and we get a velocity here of 28 this time meters per second. So we know the maximum velocity down at point P is 42 meters per second. We know the velocity will slow down to 28 meters per second at point B. And let's look back and see what this question has us doing next. Okay, so we got the speed at point B. Now, on the figure of the car below, draw and label vectors to represent the forces acting on the car when it's upside down at point B. So this one, let's be careful not to overthink this one too much. In fact, I'm going to come over to this part C, and I'm going to draw myself a little car that is upside down, and I'm going to draw my free body diagram right here. So all of the forces at point B, remember now, the first thing that there's always going to be force pointing directly down due to gravity. And that is the gravitational force that's going to be pulling down there. But also, because it is being held by the track in circular motion here, there's another force here. We got to be careful though as we write down this force, because this force, this other force, is going to be a centripetal force because it's keeping it in circular motion. But what is it that's actually providing the force? AP looks to see what is providing the force. This is the force due to gravity, and this is the normal force from the track. The normal force, which usually you think, oh, the normal force usually pushes up, but this car is upside down on the track, so the normal force is pushing down, and that is the only two forces that are acting on this car. If there was friction, it would be holding it back a little bit here, but there's no friction. Friction is negligible, so we can say the normal force and the gravitational force are the only two forces acting on this cart at this time. So, back to our question, we're almost done with number one. Now let's calculate the magnitude of all the forces identified in C. Okay, so let's come to these two forces and say, how are we going to calculate the magnitude of those two forces? Let's go ahead and get our forces back here. We've got our cart. It's got the force of gravity pulling down on it. It's also got the normal force pulling down on it. Now, we know there's a couple things. The first thing, the gravitational force, is pretty easy to solve for. The gravitational force is mass times gravity, and we know that the mass of this cart is 700 kilograms. Gravitational acceleration is 9.8 meters per second squared, and that's going to give us a gravitational force of 6,860 newtons. Now, how do we find the value of the normal force? Well, we know that this is moving in a circle, so we can say that there is centripetal force that's acting on this cart, that is keeping it down in circular motion, And that centripetal force is going to be, because it's at the top of a circle, the centripetal force is going to be both the normal force and the gravitational force acting together, right? And so if I'm looking for the value of the normal force, all I need to do is say, okay, well, at that point, I know that the normal force is going to be the centripetal force minus the gravitational force, because the gravitational force is taking care of some of it. So if I'm looking for the normal force, what is this? We remember our equation for centripetal force is mv squared over r, and the gravitational force here we solved for, which was 6,860 newtons. Let me go ahead and just do my centripetal force over here. mv squared over r. Well, do I know the velocity? Yes, I actually did solve just a minute ago for the velocity at point B. So if the velocity is 28 meters per second, the velocity was 28 meters per second, and I'm going to make sure I square that, divide by the radius of the circle, which is 20 meters, and when I do my calculation, I'm going to get a centripetal force of 27,440 newtons. So, back to my original equation, my normal force is going to be this centripetal force minus 6,860 newtons, which gives me a normal force of 20,580 newtons. And there we've solved for the gravitational force and the normal force, so I've solved for the forces that have been asked for. Last but not least, D. Supposing friction is not negligible, how could the loop be modified to maintain the same speed at the top of the loop as found in point B? Well, the only way for us to do that would be to take this loop and shrink it, right? The only way for it to have as much mechanical energy there, much kinetic energy there, as it did, because the total mechanical energy is going to be lost if there is friction. So if the mechanical energy decreases, and I want to keep the same kinetic energy, then what I'm going to have to do is I'm going to decrease the component of that mechanical energy that's potential energy. So this answer is, to maintain a speed of 28 meters per second at point B, the loop must be decreased in height in order to make up for the loss in mechanical energy due to friction. And there we have. We've solved problem number 1.